compounds of or the molecules of hydrogens that we were laying emphasis on were hydrides, in which we talked about three types. We talked about ionic. The basic characteristic of ionic were the same as generally you talk about the ionic solids, right? If you talk about ionic hydrides, then in that case you had sodium hydride or say calcium hydride or magnesium hydride. In all these cases, the ionic hydrides possessed more or less the features of the ionic solids. They're white, crystalline, and then one very important factor was that you have to remember that whenever they are in solid state, they are non-conducting in nature. Why? Because in solid state they are fixed in their lattice positions and they're not free to conduct otherwise. And the moment they get into the aqueous media, they become good conductors, right? And then we talked about say metallic or interstitial hydrides, where we did name them interstitial because they were non-stoichiometric in nature. That was one thing. Non-stoichiometry means that the ratio of the two, say the metal and the hydride, the hydrogen part of it, does not remain in integral form. It is in some fractional forms, and that you understand that how the integral part of it gets disturbed. That is because of the occupancy of your one of the ions in your interstitial positions, which was presumed earlier, but recent papers, recent findings have actually proved that also to be wrong. They're interstitial because the ratio is somehow disturbed. So scientists are looking into it as to how does it get disturbed. Another classification of hydride is that we have covalent hydrides, right? When we talk about covalent hydrides, in covalent hydrides what we basically have is um you have, yes, they are directional in nature by the virtue of hybridization, right? That you know. In covalent also we talk about three types of hydrides. One are the electron deficient hydrides, then you have electron precise hydrides, and then you have electron rich hydrides. Now the electron deficient hydrides are generally the hydrides of group 13. Like for example, you talk about BH3, which actually dimerizes into B2H6. So all these have the tendency to accept electrons because they are electron deficient, and hence your electron deficient, which are a part of your covalent hydrides form, are also known as Lewis acids. You know what are Lewis acids? The ones which can accept a lone pair of electrons, the ones which can accept electrons. Then you have electron precise are the ones which have absolutely the correct number of electrons as should be possessed by the octet rule. And then you talk about the electron rich hydrides, which are like, which have extra ions, electrons available for donation. Like for example, you talk about water, that is one of the hydrides. Yeah, NH3 is another hydride that you can talk about in case of electron rich hydrides. Okay, so these were the hydrides that we did talk about. Then what we have here is, after talking about it, now if I ask you questions like which class of covalent hydrides are classified as Lewis acids, they're on the board. So electron deficient ones are so covalent hydrides was there in the question. And then we can talk about why does water exist as an association of molecules. It exists as an association of molecules. The most simple answer that even in 8th grade would answer would be because of hydrogen bonding. But now it is asked in this context because you have extra pair of electrons which is available and which can interact with the hydrogen of the other water molecules, which can result in the bonding, right? And then you can describe the nature of the ionic hydrides. These are like general questions. They are like crystalline in nature. They are, you can say that white powdered substance and so on. That's just the physical nature. Next important compound of hydrogen that we generally can talk of is our water. And there is so much that can be talked about water because it's a universal solvent, right? 70% of earth is made up of water. Our body is actually comprising of more than 70% of water. So what we have is like, you can talk about the physical properties of water that you already know. Again, as I told you, it's like at some stage or the other you've done it all. So when I talk about the physical properties of water, it's colorless, odorless, tasteless. Now these days, many of you would not agree to it and will say that water has a particular taste. Why does it have a taste? because of either impurities or extra purity also at times. Because sometimes when people drink RO water, which is a very low hardness content, they say that the water is a little sweet to taste. And sometimes they say it's like sour to taste, thoda sa khara hai types, that depends upon the hardness. So that's only because of the degree. Otherwise, pure water is tasteless, odorless, and colorless. And whatever taste or odor that appears is only because of the impurities which are there or the salts which are present in water. It is present in the liquid state at room temperature, all of you all know that. It has extensive hydrogen bonding, which makes it really a stable molecule. The existence of hydrogen bonding is responsible for its high freezing point, high melting point, and the other characteristics, because as it is, wherever hydrogen bonding comes in, then you always talk about high melting and boiling points as well. Then the high heat, this is important. The high heat of vaporization and heat capacity, this I'll put it separately. The high heat of vaporization and the heat capacity are responsible for moderation of climate. This is what is responsible for the moderation of climate and body temperature. And body temperature of any living being or any system. Okay, remember that these are the two properties, because the rest of the properties are something that you will be able to answer or correlate to. But what are the factors which are responsible for the moderation of climate and body temperature? They are heat of vaporization and the heat capacity of water. And then because it is an excellent I just am telling you that water is responsible for the moderation of climate. You talk about humidity factors, you talk about the variation in temperature, atmospheric temperature, you talk about the difference in the body temperature. All these are related to content of water which is there. Like what are the properties that are actually relating to it? They are heat of vaporization, right? And because if your heat of vaporization gets altered according to the number of water molecules which are present, then that will alter your climate temperature as well as the body temperature. And so is your heat capacity. What is the heat capacity? It is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So that heat capacity and heat of vaporization are majorly responsible. So we are talking about the properties of water which can affect very many things. Like if I am saying that water acts as a universal solvent. It acts as a universal solvent where? Wherever it can react with some solute which can actually interact with water to either form hydrogen bonds, because wherever hydrogen bonding is possible with the solute, we say that that particular solute is soluble. So we say that whatever property that you are talking about is related to some or the other intrinsic property of water. So if I am talking about it to be a universal solvent, it may be attributed to your hydrogen bonding factor. If I am talking about the structure, it may be related to the electronic configuration factor. If I am talking about the climate and the body temperature getting affected because of water, that is because of heat capacity and heat of vaporization of water. Then yes, it is an excellent solvent. So because it is an excellent solvent, it is used for transportation processes in living beings and even in plants, because water is used as a agent for transportation of metabolites. Then alcohols, ammonia, carbohydrates all can dissolve in water because of hydrogen bonding. Then let's discuss quickly the structure of water. This again is something which is very important, but you all know about it. Structure of water. In the gaseous phase, when you talk about the structure of water, it is simply according to the hybridization factor. Now, due to the presence of lone pair, you know that the bond angle, do you want me to repeat the structure? It's like OH. A quick revision of what we've done before. Oxygen. If I have to talk about the structure, first of all, I should be able to predict the hybridization of this particular covalent structure. What were we doing? From your subjective point of view, qualitative point of view, we used to talk about the central metal atom. That is oxygen. Configuration of oxygen. 1s2. Oxygen is what? 8. 1s2. 2s2. 2p. 2, 4 and 8, right? So I know out of this only the valence orbitals will be involved in bonding. So I will talk about 2s and 2p here. This is what we used to do. This is oxygen in the ground state. I'm just revising your hybridization. This is, first we pick up the central metal atom or the central atom, sorry, and then we write down the electronic configuration of that. Once we write down the electronic configuration, it is 2s2 and 2p for, according to Hund's rule of maximum multiplicity. I will fill in first each orbital singly and then pairing will start. This is Hund's rule of maximum multiplicity. Then this is the ground state configuration. Once I talk about the ground state configuration, the next step is to employ your redox now and find out the oxidation state of that atom. What will be the oxidation state here? X plus 2 is equal to 0. So this will be minus 2. I'm in general doing it. This was like obvious that oxygen is minus 2. But you find out the oxidation state. Now what did I tell you? You have to match up your electronic configuration in such a way that the number of lone electrons or single electrons should be equal to the oxidation state. So in this case, you already have 2 single electrons. So you do not need to excite or jump any electron from one place to another. Remember hybridization? So in this case, we do not need to excite. So what will happen? This will remain as it is and the 2 hydrogens will get bonded up. The 1s1 of each hydrogen will come along with the p orbitals which are available. So the hybridization in this case will be what? sp3. So it will be sp3 hybridization, and in sp3 hybridization we know that the structure is tetrahedral. That means if one bond is on the board, then 2 bonds are coming like the pen is like placed outside the board and one is at the back of the board. So if I draw that thing out, here I have 2, what is this? This is a lone pair, this is a lone pair, these are the bond pairs. So I have 2 lone pairs and 2 bond pairs. So I can place 2 of my lone pairs just to show. I can place 2 of my lone pairs here, like you can have one lone pair here, one lone pair here, then you have hydrogen and hydrogen. Ideally speaking, the structure should have the angle of 109 degree 28 minutes, but it has 2 lone pairs and we know that the lone pair repulsion is greater than lone pair bond pair repulsion, which in turn is greater than bond pair repulsion. So using that particular rule, we know that these lone pairs are there, so they will extremely repel each other, and then these lone pair will push these bond pairs because they're also again repelling. So first of all they will push each other, so they will open up, then they will push up the bond pair further up. So as a result of that, the bond pair and the bond pair will come close to one another such that the angle between these 2 bonds no longer remains 109 degree 28 minutes. It does not remain that, and it gets reduced to 104.5 degrees, right? So this is the structure of water that you generally talk about in gas phase. Now when you talk about, say, the liquid phase, in liquid phase what generally happens is they come closer to one another because of hydrogen bonding. Now in liquid phase there will be some form or the other of the hydrogen bonding. So each molecule as per its choice will get along with some other water molecule, right? H, say O and H. You have the hydrogen bonding possible in this fashion. You can have more also, like H, O and H. So this is like in liquid state generally you get hydrogen bonded factor. So because of that you talk about the liquid structure to be like this. The only thing that you can just go through if you can, the OH bond possesses a bond length of 95.7 picometers, and the OH generally here, the bonded one, possesses around 177 picometers. I'm just giving you a rough idea that the general bond length OH possesses a bond length of about 95.7 as it is given in the book, and then OH possesses Around 177 picometers. That's like the hydrogen bonded one. So it is like the intermolecular OH separation, and this is like the intra one. It does take place. We are coming from gaseous phase, now we've moved to liquid phase. From liquid phase, now we'll move to solid phase. Alright, so now here in this case, we talk about this. Now, when you talk about the solid phase, the solid or the crystalline form is generally known as ice. So we are going to talk about the structure of ice. 104.5. In general, the angle more or less remains the same in all the three states. It is only the effect of the molecules, because the molecule as it is when you're talking about the hybridized state, that was to discuss this general structure of H2O. The general structure is sp3 hybridized only, and the lone pair remains in all these cases, because lone pair bond pair will remain the same because the atoms remain the same. So the bond angle almost remains the same in all the three cases. It is only that the intermolecular interactions will change. Now in gaseous phase, you know that each of the H2Os are located at a far away distance. So because of that they exist in the vapor state. In liquid state, because they are coming now near to one another, that is why they are like closer to one another, and because of hydrogen bonding they are like now enclosed in a liquid form. The crystalline form of it is known as ice, and at atmospheric pressure ice crystallizes in the hexagonal form. Just note down, at the atmospheric pressure ice crystallizes generally in the hexagonal form. Ice crystallizes in the hexagonal form, and then when the temperature is further lowered at very low temperatures, just note down, it condenses to the cubic form. At very low temperatures it condenses into the cubic form. And now when I talk about ice, let me tell you the structure of ice, in which oxygen is actually tetrahedrally surrounded by, it is tetrahedrally surrounded by 4 hydrogen atoms and hence the oxygen atoms. See, all of you all know that ice possesses a cage-like structure. I'm sure at some or the other stage your teachers must have taught you that whenever you talk about ice, the structure of ice generally occurs as a tetrahedral structure, such that you talk about O, H, it's like an ordered one. So here you have H, and then each of the oxygen is like tetrahedrally surrounded with, and so on, and this goes ahead. So here you have another H then, and here you have another H, and then you have O, and then you have H, and so on. So each of these oxygens, as you see, is tetrahedrally surrounded by, and remember that this hydrogen bonding is attributed to the presence of the lone pairs on the oxygen also. So what happens is, it's kind of an open cage structure. You can get that structure. Remember that, I'll just read it out for you, that each oxygen is surrounded tetrahedrally by 4 hydrogen atoms, or you can in turn say that it's also tetrahedrally in turn surrounded by oxygen atoms also. Because if this will get attached to one oxygen, this will get attached to another oxygen, this gets attached to oxygen, and this gets attached to oxygen. So in one way you can say that this oxygen is tetrahedrally attached to 4 hydrogens, or in some of the books you will even find it written as oxygen is tetrahedrally surrounded by 4 oxygen atoms. The only thing is that the distance is like greater than the OH linkage. So now here this is known as an open cage like structure that I just mentioned to you. This is known as an open cage like structure, and ice has a highly ordered 3-dimensional hydrogen bonded structure. This is what we talk about. But where the question comes in is, like we talk about when you put ice, see, we talk about the density factor when something has to float on something else, right? You talk about the density factor. Whatever is more dense will be lying lower, and whatever is less dense will come up. Now generally when you talk about the density of ice, the density of ice is considered to be lower. The density of ice is lower than that of the density of water. When you expect that in water the volume is large, because the water molecules are like at a distance, so the liquid generally you assume that the volume will be large. For the same volume, you expect the volume to be reduced. for in case of ice. Isn't that so? For the case of ice, what you assume is that the volume will be less. If volume will be less, then density of ice should be more. You getting the point? For the same mass of H2O, if your volume, you expect the volume of ice to be less. So this is like now contradictory, and that is why this question is one of the examiner's favorite question as to why the density of ice is less than that of water. See, it is attributed now to the cage-like structure. Why to the cage-like structure? You talk about ice. Ice, and when you start melting ice, what happens? Here ice has a particular element where it is tetrahedrally surrounded by 4 hydrogen bonds. They are at a particular distance where the volume, say, is a particular volume. Now what happens is, the moment you start heating it, what will first get broken up? The intermolecular hydrogen bonds. They will get broken up, because of which the cage structure will get opened up. Once it gets opened up, now this hydrogen gets a little freer from the actual ordered crystalline structure of ice to say a disordered structure. So this hydrogen can approach it from this direction also. You getting the point? So now in ice, it's a crystalline structure. I'm just explaining it to you qualitatively. Otherwise, from examination point of view, if I tell you that ice possesses an open cage-like structure and the density of ice is less than that of water, it's sufficient. And the reasons can also be discussed. Because of the open cage-like structure, you say that the density is less. But how do you relate it? That is what I'm explaining in just 2 minutes. Ice has a cage-like structure. It's a perfectly ordered one. It is tetrahedrally surrounded. All the angles and the bond lengths are set. So the moment what happens is, the moment you break it at 0 degrees Celsius, what happens is like when it starts melting, as a result of melting, what happens is the water molecules now come closer to one another. If water molecules now come closer to one another, what will happen to volume? The volume will decrease. And if volume will decrease, density will increase. So you get some hang of why the density of water should be more. Did you understand? I repeat it again. Ice has a particular cage-like structure. We are discussing a very important thing, that is density of ice is less than that of water. And you know ice floats on water, etc., etc. So now we say that that's attributed to the open cage-like structure, that you understand that oxygen is tetrahedrally surrounded by 4 hydrogen atoms, and the cage-like structure looks like this. It is an open cage-like structure where you have vacant spaces, right? It has vacant spaces in between. So it has a particular volume. The moment you start melting it, what happens is, when you melt it, the bonds get broken, the intermolecular hydrogen bond gets broken, as a result of which the water molecules come closer, and when they come closer, the volume will decrease, and if volume will decrease, your density will increase. So much so that you start at 0 degrees to 4 degrees, it goes on, the density starts increasing, and it is maximum at 4 degrees Celsius. And then what happens beyond 4 degrees Celsius? Now what happens is, the kinetic energy, because temperature is increasing, so kinetic energy will increase. If kinetic energy will increase, then the water will move at a faster pace, and then again your density will start decreasing, because now your volume will start increasing. Got it? So that is why this is like one of the most important questions, and now we can look on to the presentation here, that I've just quickly summarized what have we talked about. Just now we have just started with the structure of water. When you talk about the structure of water, all of you know the hybridization of water. This should be on your tips. It is sp3 hybridized. What is the bond angle in case of water? 104.5, which is attributed to the lone pair repulsion, which in turn is greater than lone pair bond pair, which is greater than your bond pair. Here, so the bond angle gets reduced to 104. Otherwise, what is the expected angle of sp3? 109.28. It is 109. On to the presentation here. So what you have here is, then we talk about the structure of ice. Before the structure of ice, we move on to the structure of water. And when we talk about the structure of water in the liquid phase, then what happens there is, in the liquid phase, what do we see? That there is simple hydrogen bonding, which makes your molecule comes closer to one another, which is attributed to hydrogen bonding in any form. But the moment you step on to the solid state form, what is formed is ice. What kind of a structure? It's an open cage structure which has vacant spaces in between. It's like a crystal structure. And as I told you, whenever you have arrangement of crystals, there will always be, even in a closed pack arrangement, there will be space, some vacant space will always be left, which are known as voids also in crystals. So now here, when you talk about the ice, the most important question is that ice is less dense than water. That you've understood? It is less dense than water. And then, why is that so? That is because of the breaking of the intermolecular hydrogen bonds as you start melting it. And the moment you start melting it, what happens? The intermolecular hydrogen bonds come closer to one another, and the volume decreases. And if volume decreases, then your density increases. And if your density increases, that increases till what temperature? Till 4 degrees Celsius. And because it increases till 4 degrees Celsius, then what happens beyond 4 degrees Celsius? Thermal expansion. Thermal expansion means that the kinetic energy of the molecules will increase because of the heat supplied, and as a result of that, your water molecules will start moving far away from each other. Then what happens at 4 degrees Celsius? Because 0 to 4 may be your thermal factor is playing a role, temperature is increasing. But that is why I have written it here, that the two effects, the thermal expansion and the breaking of the hydrogen bonds, just balance out each other at 4 degrees Celsius to give you the maximum density at 4. You've understood both the methods, right? One is like the thermal expansion and the other is hydrogen bonds. Breaking of hydrogen bonds gets your water molecule closer, which decreases the volume, increases the density. And when your density comes closer, it is the thermal expansion which predominates, because then volume will increase. But at 4 degrees Celsius, both these factors balance out each other. Okay? Then we move on to the density of water we've discussed, the chemical properties of water. See, by and large, you know that water possesses three properties. What are those three properties? Those are, you have amphoteric nature of water. What is the meaning of amphoteric? The ones which can interact both with acid or base, and in some of the cases you talk about amphoteric nature, which can act both as an acid as well as a base. Then there are many redox reactions. In redox reactions, you know that water can act both as a reducing agent also as well as an oxidizing agent. And then we'll talk about the hydrolysis reaction, where you know that it is the breaking of water, as the name suggests, hydrolysis. So it is the lysis of hydro, so it is hydrolysis reactions, where you will talk about the breaking of water to interact with the molecules. And the fourth one is hydrate formation. So hydrate formation is wherever you have the formation or the attachment of an H2O to a molecule directly. It can be in the form of a ligand. We'll talk about what ligands are, or it can be in the form of water of crystallization. Now, water of crystallization you must have heard of also. Sometimes when you deal with more salt, if you've all taken it up, it has 24 H2O. You write the formula as dot 24 H2O, which means that there are water of crystallization. Where do these water of crystallization exist? These water occupy the interstitial spaces and they sit there. Alright, so let's talk about them in details. Write down some of the reactions when water acts as a base. First, let's talk about the amphoteric nature quickly, where water just acts as a base. So I'll just put down the reaction for you. Here what you have is H2O plus H2S, and you give out the reaction here. I'm telling you that this acts as a base. If it acts as a base, what will it do? It will accept the H plus. I hope you remember the acidic and basic nature. What are, if you talk about the acids are the ones which can give H plus, and base are the ones which can accept H plus. And in terms of lone pair of electrons, base are the ones which can donate a lone pair of electrons, and acids are the ones which can accept a lone pair of electrons. So H2O plus H2S, that now what will that give you? If it is a base acting as a base here, it will form H3O plus and plus HS minus. Right, next you can write down plus here. Then the next one, say it reacts with HCl. That also you know. When it acts as a base, you can write down these reactions on your own. Then when water acts as an acid, you can essentially make it react with a base. If it has to act as an acid, you can make it react with a base. And then there is a reaction called autoprotolysis. Autoprotolysis is when water reacts with water. So then one molecule of water will act as an acid and the other molecule of water will act as a base. This autoprotolysis is also known as self-ionization because it is creating ions of its own by reacting with itself. So this is also known as self-ionization. So here what we have is, you have H2O liquid plus another H2O liquid, and that will exist in equilibrium to form the ions. So here what will you get? H3O plus Cl minus. Here OH minus plus NH4 plus. Remember that here NH3 is already is a base. So it will accept the proton and you will get OH minus and NH4 plus. Say according to the Bronsted acid base concept, you call this acid, and if this is your base, again your 11th class revision, this is your acid, this is your base, and what you will have here, this will be called now a conjugate, because acid ka you will get the conjugate base, and now this base is now, remember that from the acid you always get the conjugate base, which is 1H minus, not 1H minus of 1H, and from the base you get conjugate acid, which is addition of one hydrogen atom to it. So along with a plus, H plus. Then for the self-ionization, that's very simple. You have H3O plus plus OH minus. So you talk about the, and water is like always neutral, where the pH is considered to be 7 only at 25 degrees Celsius. pH of water, all of you all know, is 7. That's a neutral pH, yes. That exists in equilibrium with your H3O plus and OH minus. So what is H2O plus H2O? It's water. Water plus water is water. Water plus milk may make it milk. So what I'm telling you is like water plus water will make it remain as water, but that self-ionization process is very much on. So much so that the moment you add, now you have H3O plus and OH minus existing in equal concentrations. So here the acid, you cannot differentiate between, because otherwise one water molecule and the other water molecule are indistinguishable. You cannot differentiate between the two. So you have H2O plus H2O giving H3O plus OH minus, and that is what is the significance of these arrows. These are in equilibrium. So the moment you try to disturb the equilibrium, only then it will get disturbed. Like for example, now if it reacts with NH3, now NH3 will take up an H plus from here. Say, adding on to your question only. What we have is, what we have here is, supposedly now if it interacts with NH3, so in NH3, what will happen? It will give you NH4 plus because it's a base, plus water, and your OH minus remain as it is. So what you were getting was NH4 plus OH minus. So the basic purpose of self-ionization is like the ions are ready and willing to be immediately reacting with your base or acid. So that's just portraying that. So it's one and the same thing. It's just a vicious circle. Then alright, for the oxidizing agent, I am just writing when water acts as an oxidizing agent, so that you get hint and confidence. Then you have another one, water acts as a reducing agent. Generally, when it reacts with alkali metals, you know alkali metals will get oxidized. So, water there will act as an oxidizing agent, and when it acts as a reducing agent, then you can make it react with any of the non-metals like F2. So here they will act as a reducing agent. It acts as a reducing agent. Water is oxidized to O2. This is important again, something that you've done so many a times, is oxidized to O2 during photosynthesis. Do you want me to write the photosynthesis reaction for you? Photosynthesis, so that is 6 CO2 plus, you were talking about the reverse, that is the respiration. Yes, 6 CO2 plus 6 H2O gives you C6 H12O6 plus 6 O2. But remember that in this case, water is oxidized to oxygen. So water is acting as a, if it is if in itself is getting oxidized, then it is getting as acting as a reducing agent. Remember, in all these cases, what you have here is you get NaOH. If you get NaOH plus, you will have H plus, right? What will you get? NaOH will become NaOH plus, you will have NaOH plus H2. Because now water is acting as an oxidizing agent, it will in itself get reduced from +1 state to 0, and your sodium will get oxidized from 0 to +1 state, right? So here your water is like acting as an oxidizing agent. Remember that an oxidizing agent is the one which itself will get reduced. So your water, in water, hydrogen is getting reduced from +1 state to 0 state, and your sodium is getting, it is oxidizing your sodium from 0 to +1 state. That much of chemistry you have to remember. Now if it is acting as a reducing agent here, then definitely it in itself will get oxidized. So if it will get oxidized, it will form, and what you are getting with your F is like you will have 4HF plus O2 is what the reaction gives you. So what is happening in this case? Your H from +1 remains as +1. So what is happening to the oxygen? Oxygen from -2 is going to, so that means now water, because H is remaining the same, you will see water is getting oxidized to oxygen. Got the point? Now water is getting oxidized to oxygen. So that means water is acting as a reducing agent. Please remember this. Whenever water is getting converted into oxygen, you say that water is acting as a reducing agent, because oxygen is getting oxidized in itself from -2 to 0. But reducing agent, what work does it do? It will reduce the other species. So other species is getting reduced from 0 to -1. So using this principle only, now we are talking about the photosynthesis. Water is getting converted to oxygen. So water is getting converted to oxygen. So water is acting as a, correct? So we do not have to apply mind to each and every oxidation state here. Just state that water is getting now oxidized to oxygen, and so water acts as a reducing agent. And something that I'm not written in the photosynthesis reaction very importantly is like and yes. Okay, so then we talk about the hydrolysis reaction. In hydrolysis reaction, you know that water will get broken up and it will interact with your species. So let's write down some of the hydrolysis reaction. Remember that this question has also been asked many a times, that your water acts as what? An oxidizing agent, as a neutral medium, or a reducing agent for this. Can't understand first equation. It is balanced. Is there? It is not balanced. Is there any reason? This first equation, balance it. 2 water plus Na plus Na. The point here was that water reacts with your Na to give you NaOH and H2. We were just discussing the oxidation state. But if you have to balance, just balance it. You will have 2 Na and then you have 2 NaOH, right? And 2 2s are 4. No, it's done. 2 plus 2, 4. Balanced. Right? Now we come on to the hydrolysis reaction. And remember that the point here in the previous case was just to remember the amphoteric nature of, no, now the amphoteric nature was when it reacts both with acid as well as base. The next thing that we were laying emphasis on was like its participation in the redox reaction. In the redox reactions, why do we talk? We talk about oxidizing reducing agents. So water can act both as an oxidizing agent also as well as a reducing agent, which you already knew. So the point that I wanted you to remember from here is whenever your water is getting converted to oxygen, say that water is acting as a reducing agent. Why? Because it is getting oxidized to oxygen. And then we laid emphasis on this reaction saying that here water interacts with Na to oxidize it to +1 state. So again water here it is acting as a reducing agent. Why? Because it is oxidizing. The one who oxidizes the other is the oxidizing agent, and what sacrifice will it do? It will reduce itself. So it is, sorry, it is an oxidizing agent and it will, water interacts with Na to from 0 to +1 state, so that means it acts as an oxidizing agent. And what is the sacrifice that it does? I repeat, it will in itself get reduced, so it acts as an oxidizing agent. The entire redox chapter is all about this, the intermingling of these words. Alright, then we talk about the hydrolysis reaction. We have say P4O10, when it interacts with water. You tell me what will be formed. Generally they give rise to their respective acids. So you can talk about that in that form. When water generally reacts with the non-metallic oxides, this also you've done in 10th standard. When water interacts with non-metallic oxides, it gives rise to the acids, non-metallic oxides. And then it gives rise to bases when it reacts with carbide, hydrides, nitrides, phosphides. So if you talk about CaC2 plus say water, then it gives you H2 plus 2 water, and then you have some more reactions if I talk about. Alright, aluminium nitride, because I've talked about hydrides. Remember that when water interacts with carbide, hydrides and nitrides, then in that case we generally talk about the formation of the respective bases. So here you have, when it interacts with this, what is going to get formed? What acid of phosphorus? Phosphoric acid, so you get H3PO4. H3PO3 is your phosphorus acid. You can balance this reaction also, and if you want me to balance 6 and 4, it's given in the paper itself. Then this will be your H2SO4 simply. The reaction is like already balanced. Then you have CaC2 plus 2H2O. So if you have metallic carbides, hydrides or nitrides and they react with water, the hydrolysis will result in their formation of respective bases. So what you will get is, I'll write the primary compound. You will have CaOH twice, plus you will again get CaOH twice in the next case, and in the next case what will you get? ALOH thrice, plus whatever is like left over. right? So here we are talking about the hydrolysis reaction where your water is getting broken up to form the respective acids and bases. Generally, when it reacts with non-metallic compounds, it always results in the formation of acids. When it interacts with metallic compounds, it results in the formation of bases. Then now let's talk about the fourth case, that is the hydrate formation when we are talking about the formation of water. So the slides that I had put here all had the water flowing to keep you awake, but unfortunately they're not playing it here. It's not getting played. Then we talk about hydrates formation. Because for hydrogen chemistry you have to do a lot of reactions. So it's all about understanding something that you've already done. So hydrates, now let's talk about hydrates. First of all, hydrates can occur in the form of ligands. Now you must be wondering what ligands are. I will just tell you, this is a part of your coordination chemistry that you will be doing in 12th standard now. Alright, let me just talk about this first. What happens is, there are some compounds which are known as coordination compounds or complex compounds. What happens is, they are generally the ones which are formed from the D block elements. Now D block elements are the ones which have what series you have done till now is like, you've done the 3D1 series to 3D10 series. Hope you remember, that was Ker, Tai, Wa. Very nice, you sing beautifully. Fiku, Niku, Zn. Right? So this is what we had done before. So this is all you know. What happens here in all these cases, you have vacant d orbitals available with all of them, which are willing to accept a lone pair of electrons. Do you get that? Because if I talk about scandium is like, you have D5, right? And you have D1. It can accept full pair of electrons in its vacant d orbitals. So one thing is that their size and then the presence of vacant d orbitals make them suitable for formation of such compounds. Normally what happens is, if you have NH3 is a base. It has a lone pair of electrons. It can accept still coordinate covalent bonds. It's a covalent bond? But when we say it forms a coordinate covalent bond, means it is accepting some other atom to interact with it, and that comes in as H, and then it forms NH4 plus, right? You getting that point? Now here in this case, why did it not form a coordination complex? It did not form because it did not have a full vacant orbital available to it. Whereas in this case, you have a vacant orbital available. Right? Do you understand that? You will be doing a full chapter on it. So you will become much more intelligent than what I am talking about right now. So it has a vacant orbital. So each of these ligands have a capability of donating a pair of electrons. Water has, right? Similarly, there are many more ligands which are available, like Cl minus. Cl minus had one electron as the last one, NP5 hota hai na, configuration. So it has one electron in the last orbital, and then when it accepts, it carries one full electron pair. So that electron pair can be readily donated as ligand. So Cl minus can act as a ligand. Similarly, NO3 minus, you can have a number of them then. So you can have a number, OH minus. All these can act as ligands because they can donate a pair of electrons to your vacant d orbitals. You get that? Or generally, sometimes in many of the books, you will just write full water written in each one of them. That depends of how you're representing. Did you understand this? So water can act as a ligand because of the capability of donating a lone pair of electrons. So here you are talking about the D block elements forming the coordination complex, and this is now that I have talked about it. Let me just tell you one more feature before I move on to the next. It can also act as a ligand. No, 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 no. Ligands क्या है? ये है ligand. और डी ब्लॉक क्या फॉर्म कर रहा है? सेंट्रल एटम, जो जो सेंट्रल मेन एटम है, द कोर ऑफ योर कोऑर्डिनेशन कॉम्प्लेक्स or the coordination compounds remain your D block elements. It generally remains your D block elements. And why D block elements? That I have told you, because of small size and presence of low lying. Low lying means energy उनकी low होती है, और जो भी incoming ligands हैं उनकी energy high होती है, तो they can easily come and donate a pair of electrons. They have the presence of low lying vacant D orbitals. Complex, right? So now these can act as a ligand. Understand? So there are many other, I am telling you, there are many other ligands which are possible. One of the possibility now, because we are talking about hydrogen and its chemistry, one of the possibility is that we talk about H2O. So H2O can act as a ligand. The only thing is I wanted to make you understand the meaning of this coordination complex. कि यहाँ पे एक central atom होता है, वो generally D block होता है. D block क्यों होता है? Because they are low lying, they have small size, they have vacant d orbitals. Then these can act as a ligand. Why? Because they are capable of donating a pair of ligands. What is the benefit of having this coordination complex? I tell you, you are doing a double salt. Double salt is like a more salt, FeSO4, NH4 twice, and SO4 and then dot 24H2O. जब उसको पानी में डालते हो, each of the FeSO4, NH4 twice, SO4, each of them get broken down into their respective ions. You will have Fe2 plus, you will have SO4 2 minus, you will have 2NH4 plus, SO4 2 minus, and so on. So the double salt loses its identity completely, right? The double salt will lose its identity completely. But a coordination complex, let me just take up another example. If I have a coordination complex like FeH2O 6 times Cl3, if I have a coordination complex like FeH2O 6 times Cl3, then in that case it will get broken up only into, what was it, Cl3? So it will get broken up into 3Cl minus, and the coordination complex remains as it is. So the coordination compound does not lose its identity even in aqueous media. बात समझ में आई? Double salt क्या करता है? It loses its identity because it gets completely dissociated into its ions. You all know more salt. I took that example. Then when you talk about the coordination compounds, ये मैंने समझा दिया. Whatever is within the sphere is your coordination complex, because all these are attached to the central atom. When you put it in water, this, and I wrote the total complex as this Cl3. This is known as our primary valence. This is known as our secondary valence. So इसके अंदर से सिर्फ primary valence अलग होगा. जो मेरा coordination sphere है, that will remain intact. This is an advantage of the having coordinate or the property. Because they are like attached. They've already donated a pair of electrons, and the bonding is like strong enough to maintain that complex stable. No, then you can, there are several reactions which are possible, because of which you can, not in the aqueous form. Aqueous form में क्या होता है? जब भी हम ionic solids की बात करते हैं, that's what I have been talking about always. What is the example that I take? NaCl. We take NaCl solid form, it remains as it is. पानी में डालते it becomes Na plus and Cl minus. So is the case with the double salts. As it is, it remains as a salt. The moment you add salt to water, I have told you one thumb rule. All salts are strong electrolytes. Strong means that they completely dissociate into the aqueous, into ions in aqueous media. So here when you talk about this complete coordination complex, the primary valence will get separated of whatever is outside the coordination sphere, but the coordination sphere remains as it is. So the primary valence means it will have plus 3Cl minus. Here it is. There is. No, the primary valence, this is called an ion. This is the entire coordination compound. Right? If you can call it salt because this has a positive charge of 3 plus 3Cl minus. But the coordination sphere remains as it is. And we call it a coordination compound. The rest of it, just wait and watch. You will be doing it in 12th standard. A very simple and a scoring chapter. Because if you've got it now, I think you will be able to pick it up. Then the next is like not only as ligands, water also, the hydrates also occur in the form of water of crystallization. Water of crystallization is like the water molecules occupies the interstitial spaces, and then you have compounds in which water molecules are hydrogen bonded to certain oxygen ions also. So that's like fine. So it can act as, your hydrates can be in the form of ligands, it can be in the form of water of crystallization, or in certain cases it is some kind of a water of crystallization only where it is directly bonded to the oxygen of the oxygen of the rest of the molecule, or any of the oxygen atoms. I'll give you an example for that. That is like you have Cu H2O 4 times the whole 2 plus SO4 2 minus dot H2O. And as I told you that copper is again 3D. Now you understand the meaning of this square bracket. What is this? This is a coordination complex. And then you have 2 plus here. So in order to satisfy that, you have a 2 minus. This is your primary valence. Right? That will always get satisfied. So now here in this case, what happens is your water inside, this water is bonded to the water inside. This water is bonded to the water inside and then in turn bonded to sulfate. So this is like kind of a water of crystallization, but it is simultaneously bonded to the water inside as well as to sulfate. But this bond can be broken down on heating simply. Now if I ask you simple questions, why do alcohols dissolve in water? Just tell me as I am rubbing the board. Why do alcohols dissolve in water? Alcohols? What are alcohols? ROH. Why do they dissolve in water? Because of? So why do you have to think about it? I want you to be spontaneous. I understand hydrogen chemistry is like hydrogen, hydrogen and hydrogen. So that is why I wanted the water to be flowing. If you can see in the background, this water should have been flowing. It's not flowing. But please, you keep flowing in the class, not in the other way. Okay, so which properties of hydrogen are responsible for moderation of climate and body temperature of living beings? That's much better. Yes, there. Which properties of hydrogen are responsible for moderation of climate and body temperature of living beings? Which property of water is responsible for moderation of climate and body temperature? High heat of vaporization and heat capacity. Repeat. Repeat. High heat of vaporization and heat capacity. Repeat. High heat of vaporization and heat capacity. They got nervous probably. Compare the density of ice and water, which has more density and which is ice is less than that of water. So only subjective questions. Does water gets oxidized in the process of photosynthesis? It gets oxidized too. It acts as a. Okay. So then we talk about the next case. We have. Then we talk about now, just to shift you from here to there so that you keep your eyes moving from one place to another. Now we have types of water. This again, you know, what are the types of water? You have hard water and soft water. Hard water is hard, soft water is soft. That depends on the salts which are there. So hard water is the one that does not produce lather, you know that. And you can test it for yourself in different regions of Delhi. Right? So hard water does not produce lather with soap easily due to the presence of calcium and magnesium salts. Which one? In the form of bicarbonates, chlorides and sulfates. That is like, now we'll talk about bicarbonates, chlorides and sulfates separately also. There are different sorts of the calcium and magnesium which are present in water generally. Then what you have is, then the hardness is defined on the basis of whether which salt is like put in water. Then the next one is soft water, is the one which produces lather. It's good for washing clothes, doing so many other works. So they are free from the soluble salts of calcium and magnesium, and that you know, right? If we check on to the next slide, then we see that there I've talked about the types of hardness. If we talk about the type of hardness, now we know temporary hardness. Temporary, temporary is temporary, permanent is permanent. Temporary hardness is due to the presence of bicarbonates. And you know that when you write down the reaction, first of all, look onto the board. I'll just put down the reaction that's generally carried out in the laundry. You have, say, calcium or magnesium salt, Ca2 plus or Mg2 plus, that reacts with soap. Soap is generally what you have, the sodium or the potassium salts of long chain fatty acids. This is again very good, COO, Na. So what is this known as? Sodium stearate. That is the sodium salt of long chain fatty acids. This is known as sodium stearate. And what you get here is you get the metallic part of it interacting. What happens in case of hard water? You have the calcium and magnesium salts which are present. When your calcium and magnesium salts are present, they will interact. This 2 plus will now interact with the rest of it to form C17 with the minus part. What is your minus part here? This is C17H35COO minus Na plus. It is like the carboxylic acids, right? So the H is replaced by an Na here. So you have C17H35COO minus. So if you have 2 plus, so this becomes twice M. So what happens is, when your soaps are like made to interact with those salts of calcium and magnesium which are present in hard water, it produces a precipitate which is also known as scum. It produces an insoluble precipitate, and this insoluble precipitate, as a result of being produced, interferes with the action of soap, because the soaps have now changed their formula. So you have plus, you have 2Na plus, which is of course soluble in water. So there is no lather produced. And then another harmful effect of hard water is that it is really harmful for boilers. Yeah, so it causes scaling. Why? Because the insoluble, the salts get deposited onto the boilers, and as a result of that they spoil them. And this is again something, if you keep boiling water in your boilers, you will time and again, the simple ones that are available, you will see that they will spoil them after a period of time because of the scale that that is produced because of the insoluble salts. Soluble salts which actually turn out to be deposited on them. Then we've discussed the type of hardness, that is temporary and permanent hardness. First we talk about the temporary hardness. Temporary hardness was the one in which you have the salts of bicarbonates. And when you talk about the bicarbonates, remember that temporary hardness can be removed easily. Temporary hardness can be removed by simple boiling. We are talking about removal of temporary hardness, because temporary is temporary. It can be removed by simpler methods like boiling. What happens is, even if you have any of the bicarbonates, say MgHCO3 twice is the formula of the bicarbonates, what is done is, like, you simply heat it. It will give you an MgOH twice precipitate plus 2CO2, which is like generally soluble. So carbon dioxide is like evolved outside. You get rid of the bicarbonate salt very easily. And MgOH twice is a base. So this does not precipitate out, so you should not be drawing that. Generally this arrow shows that your salt is getting precipitated out. So you have the bicarbonate, you simply boil it, and you get MgOH twice plus 2CO2. Then similarly you can write it down for the calcium also. For calcium, you do not get calcium hydroxide directly. You get calcium carbonate plus water plus CO2. This is again on simple heating. the one of the methods of removing temporary hardness. Then the second method for removing temporary hardness is your Clark's method. And the moment you are talked about the Clark's method, remember Clark, the moment you are talking about Clark's method, remember it should be related to slaked lime. Clark's method is your treatment of the hard water which is temporarily hard with slaked lime is calcium hydroxide. So you are going to make your bicarbonate, say CaHCO3 twice plus CaOH twice, that's your slaked lime. It will precipitate out your calcium carbonate plus water. That's the Clark's method. When you talk about the magnesium salt, MgHCO3 whole twice, that reacts with your calcium hydroxide. That gives again a precipitate of calcium carbonate plus MgOH twice plus carbon dioxide. Okay, so remember boiling is like a simple boiling which is generally producing the hydroxide or calcium carbonate, and in the Clark's method you get calcium carbonate in both the cases and magnesium hydroxide in case of magnesium bicarbonate. In both these cases it is easily removable. What you need to remember from entrance examination point of view is that your boiling is like boiling, simple boiling. That heat and carbon dioxide is involved in both the cases which gets removed off. And then Clark's method, you have to remember the reagent. What is it? Slaked lime. What is that? Calcium hydroxide. Then let's talk about now the permanent hardness, which is basically due to the chlorides and sulfides of calcium and magnesium. So in order to remove the permanent hardness, one needs to do a treatment with washing soda. So for permanent hardness, now we are talking about, first is the treatment with washing soda that we've already mentioned. Washing soda is your Na2CO3, and these names are to be remembered. Slaked lime is calcium hydroxide, washing soda is Na2CO3. So what will happen? Now you are intelligent enough to write down the reactions. It is simply a double kind of displacement. So you can write it down. I am not writing down the reaction for you. You all are intelligent enough to write it. So if you remember just the method, you can write down the reaction on your own. So in both the cases, you get the carbonate, because what is our purpose is to actually dissociate these and disrupt these salts. So what we get is, in this case, you get insoluble carbonates which see now. So what we get is CaCO3 plus 2NaCl. What is the benefit now? Permanent hardness was because of calcium chloride. Calcium chloride we added washing soda. What happened on adding washing soda? We got calcium carbonate. It got precipitated out. So precipitate can be separated out. ठीक है? Precipitate को बाहर निकाल दिया. पीछे क्या बचा? Normal water plus NaCl. That's a useful salt. It will not harm it. Then the next is like in case of sulfate now. In case of sulfate now we'll get sodium sulfate Na2SO4 plus magnesium carbonate. Again magnesium carbonate will get precipitated out. So the carbonates will form a precipitate. Precipitate can be separated. पीछे क्या बचा? Sodium salts are generally soluble and harmless. So you have sodium sulfate which will get dissolved in water. And you need in trace amounts all of these elements. You know that their body requirement is that you need some macronutrients, some micronutrients. So they all form a part of micronutrients. So some bit of it should always go into the body also. So that is why in many of the cases, RO sometimes is considered to be harmful because it sometimes does not allow all the salts to come in water. You must have heard of that. So you should, even hard water is good for the body because some salts should be reaching your body, but not to the extent of harming your body. So alright, let's move on to the next method, which is an important method, that is the Calgon method. The second method is Calgon method. First is clear to everyone. Washing soda, so just try and memorize it right here. Calgon is actually the name of sodium hexameter phosphate. So that is Calgon is sodium hexametaphosphate. So hexametaphosphate is your P6O18. Please remember this formula. Calgon is sodium hexametaphosphate, and it is the reaction with Calgon now that is going to remove the permanent hardness. So the permanent hardness, again, you just check it out. What we have is, we need to remove those salts, the metallic ions, which are like the hard ones, that first gets dissociated into 2Na plus Na4 P6O18 2 minus. This is what is formed, and then this Na4 P6O18 2 minus interacts with your M2 plus to give you this, forms your Na2 MP6O18 2 minus plus 2Na plus. The complex anion actually keeps the Mg2 plus and Ca2 plus ions in solution. You have 2 minus. This is the complex anion. Remember that for your entrance examinations, you will not be memorizing these equations at all. You just have to go through. So now in Calgon process, it results in the formation of an anion. That anion interacts with your metal and it extracts the metal into its sphere to form this. So it is this complex anion which now holds it traps your calcium or magnesium into it, and what you have will be the sodium salt. Sodium salt will be soluble in water and harmless. Then another method is, the next one is like, we talk about the ion exchange method. See, ion exchange, as the name suggests, is like exchange of ions. So in that case, what we generally do is, it works on the principle of exchanging ions responsible for the hardness of water, because basically we want to extract. In one sense, अगर आप पीछे वाले methods भी देखो, तो they were in some way or the other exchange of ions only, but you call them double displacement reaction, displacement, and so on. So here when you talk about this ion exchange method, like here when we've talked about the treatment of washing soda, it's treatment with Na2CO3. When we talk about the treatment with, or the Calgon's method, we are talking about sodium hexametaphosphate, that is Na6P6O18. So Calgon से नाम याद आ जाना चाहिए और फॉर्मूला सामने फ्लैश हो जाना चाहिए. So that is Na6 P6O18. Very good. So then the third one is the ion exchange method. Now when you use the ion exchange method, it should immediately come to your mind that we are making use of zeolites, right? So ion exchange method is related to your zeolites. Our zeolites are also known as permutate. So this method is also known as the permutate method or the zeolite method. And zeolite is your, please note down, zeolite is your hydrated sodium aluminium silicate. Sodium, aluminium, and then silicate. So SiO4. So the zeolite that is used are the permutate also. It is also called permutate. That is used is sodium aluminium silicate. So remember the formula here in this case also. So it is what? Zeolite is NaAlSiO4. So now we'll talk about the interaction with NaAlSiO4. So you have, say, let me just take this as Z. So NaZ reacts with your calcium or magnesium salt, the hard one, that may be a chloride or a sulfate, and forms your plus 2Na plus. So now the cations are exchanged with sodium. The cations are exchanged with sodium. So very clearly we see that whenever we employ a zeolite, that zeolite would interact with metal to exchange your sodium ions, as we were doing in the previous case only. But each of these methods is associated with a reagent that is more important. Otherwise, you know that a sodium salt is getting formed and that sodium salt is going into water. And your calcium or magnesium is being extracted, and we are breaking that salt which was producing a scum or was like harmful or was causing the scaling, calcium chloride, sulfates, bicarbonates, and etc. Then what happens generally in this case, the zeolite is being used up. Let me tell you, zeolite is not just important here for the removal of hardness, but otherwise also zeolites has a number of industrial applications. So they are also again important. So what can be done is this zeolite or permutate can be regenerated also. क्योंकि इसमें से गया क्या है zeolite में से? सिर्फ सोडियम. तो किसी भी सोडियम कंपाउंड के साथ उसको रिएक्ट करा दो, make it react with a base. So if this MZ2 now reacts with a base, your permutate can be regenerated. And normally वो वाला method we consider to be the best, in which जो side product है या तो वो बाहर निकल के चला जाए, या फिर it can be regenerated for some fruitful use. There are two methods you will be doing this year in chemistry, in organic also and otherwise also. The best methods which are considered are the ones in which either you get the main product in a very good yield, or side products are gases, so they will go into the air. Or if you're utilizing some very important compound, it may be expensive, it is industrially very important. So when you're using a main compound, it can be regenerated. And here in this case, it can be regenerated. The regeneration of permutate can be carried out as the zeolite can get exhausted because the whole sodium zeolite is being used. It is regenerated by making or treating it with aqueous say NaCl solution also. It can be regenerated by treatment with aqueous NaCl. तो इसको अलग करेंगे हम. We'll separate out the MZ2, make it interact with NaCl. तो हमारा कैल्शियम या मैग्नीशियम जो भी था वो वापस क्लोराइड बनाएगा, and we'll get back our NaAlSiO4, NaZ. Whenever you have the ionic form of it, if I have A plus B minus plus X plus Y minus, there is always a double displacement reaction that occurs between the ions. So that is A plus Y minus, and you will get X plus and B minus. ठीक है, ये तो मिलेगा ही मिलेगा. अब क्वेश्चन है रिएक्टिविटी का that you are asking. The question can be catered to as, जैसे if you have A and you have B2 plus, right? Now if your A is more reactive than B2 plus, only then it will form A2 plus plus B. If the reactivity is like A, C, D, B, so A is placed above B. What a weird way of telling. A is located above B, so it is more reactive. अगर वो more reactive है तभी वो उसको aqueous solution से displace करेगा. आपने अपने metal को as it is डाला और वो aqueous solution से उसको displace करेगा ही करेगा. तो यहाँ पे तो wherever your A is, it will displace the other because there's a competition. Whatever you have, I want that. But here, when your A is in the atomic form and B is in the ionic form, तब सिर्फ वही वाला atom ion को replace करेगा जो more reactive है, जो more the activity is more for whichever atom. If it was like B plus A2 minus now, A2 plus now, there will be no reaction. Why? Because B is now less reactive than A, and it will not displace it from its aqueous solution. क्योंकि here A2 plus मतलब इसके साथ कोई anion भी है. A2 plus का मतलब है A2 plus के साथ कोई anion भी है, right? तो वो उसको anionic form से displace नहीं करेगा. It will just not change it. That's like the entire thing. So whenever you have when you have a salts, generally that interaction happens. Okay? So we were on which method? Ion exchange method. Ion exchange method is mainly because of zeolites or permutate. What is the formula for zeolite? NaAlSiO4. And NaAlSiO4 is known as sodium aluminium silicate. Alright, and then we have the sodium aluminium silicate interacting with the calcium and magnesium salt. I could have written MCl2 also or MSO4 also, बस उसमें सिर्फ यही आ जाता है यहाँ पे आपका SF4 या जो भी you would have got that. And here what is the benefit of using the zeolite? It can be regenerated by simple reaction with any salt solution. Okay, so regeneration of permitted. Now the next method is the synthetic resin method. In synthetic resin method, we it's superior to the zeolite method. Why are you doing all these methods? One method is better than the other. So because they remove all unwanted cations or anions. It generally removes all the unwanted cations or anions. So here we have see synthetic resins are insoluble. First of all, I am trying now talking about synthetic resin method. Synthetic resin method, and in synthetic resin method I will talk about two. One is the cation exchange resin and the other is the anion exchange resin. But you should first understand that what are synthetic resins. These synthetic resins are insoluble polymeric solids. They are insoluble polymeric solids. Do you know what are polymers? Monomers, and monomer is like one unit which keeps repeating itself to form the polymers. So you have insoluble polymeric solids here, and having a giant, generally the polymeric units involved here is the ones which have a very big hydrocarbon network, right? So let's talk about the cation exchange method first. We talk about the cation exchange resin. In cation exchange resin we have a large organic molecule with SO3H. देखो organic molecule तो both cases में है. You have a cation exchange resin and you have an anion exchange resin. So in both these cases you have a big polymer which has a big hydrocarbon network. Hydrocarbon network means we are talking about organic part of it. So here your organic molecule is with what group? SO3H group, and they are water insoluble. They are insoluble in water. Alright, and in anion exchange resin I will simultaneously put so that you remember. These are the main things which are to be remembered. You have that giant hydrocarbon network which has the functional groups which play a role are the NH2 or the OH minus group. So you get it? In the cation exchange resin it is mainly the SO3H group, the sulfonic acid group, which is majorly important, and in an anion exchange resin you have the H2. So first ion exchange resin gets, see, first the ion exchange resin, that is R SO3H, get exchanged to RNA after treating it with NaCl. See, the first treatment is you have your RSO3H. R means a big giant organic moiety which is like a great hydrocarbon that is there. It reacts with NaCl to form your RNA. And then what happens after treating it with NaCl? This RNA now exchanges your Na plus with Ca minus, because we want our Ca plus, Ca2 plus and Mg2 plus to come out. So this RNA then reacts with your M2 plus to give R2M plus 2Na plus, and R2M plus 2Na plus. So this is the main reaction where you know that your hardness is getting removed. And what is, in order to obtain pure demineralized water, what it does is RH जो भी hydrocarbon है हमारा, that reacts with to form Mr2 plus 2H plus. The cation exchange is used this cation exchange is used. So whatever hydrocarbon you are left with interacts with M2 plus to form, from all cations or anions, it will just get extracted and you will have 2H plus. So these are the main reactions for your cation exchange resin, because you get pure demineralized water which is free from all soluble mineral salts, which are there. The cation exchange in the H plus form is used here. Okay, then when we talk about anion exchange, first of all, for the anion exchange, I'll just put down the reactions. You have RNH2 plus water in equilibrium to first form a kind of a complex, that is RNH3 plus and OH minus. That's the salt that is formed. And this RNH3 plus OH minus interacts with X minus to give RNH3X plus X minus plus OH minus. So your X minus, the chloride or the sulfate, is getting separated out here. And then you can also put down this reaction with Cl minus. You can write it down, RNH3 plus OH minus plus Cl minus. ऊपर वाले basis पे you can easily write it down. In the above reaction, OH minus basically exchanges, OH minus ions are liberated. So you have OH, so basically H plus plus OH minus, that yields your water. So these are generally the two methods of the cation and the anion exchange resins that were used. The major thing that I want you to remember here is cation, both a synthetic exchange resin, matlab we are talking about some organic molecule, and that organic molecule has some group attached to it. For the cation exchange resin, what is the group that is attached? Sulfonic acid, SO3H. For the anion exchange resin, you have NH2 or OH minus. Now here in this case, you just have to remember the very first step in cation exchange is we extract the sodium part of it. So we make it react with the sodium salt like NaCl to exchange our SO3H with Na. Once that is done, then we exchange our calcium or magnesium with it. So cation ka exchange ho gaya, calcium or magnesium is exchanged. So cation gets exchanged and we get R2M plus. But in order to get totally demineralized water, whatever part of R2 that is left will be forming the hydrocarbon, and that hydrocarbon will interact with M2 plus to yield your cation 2H plus now, which will interact to form water, because 2H plus remains in water. Then in case of anion exchange resin, I told you that the groups that are important are NH2 or OH minus ions. So like for example, we start with the amine part of it. Big hydrocarbon with an NH2 interacts with water to form a kind of a salt, that is RNH3 plus OH minus. Now your RNH3 plus OH minus interacts with your X minus, which is either the chloride or the sulfate, Cl minus or SO4 minus. It interacts with that, and as a result of that, ये जो OH minus last में attach हुआ था, that anion will get exchanged with the Cl minus or SO4 minus, and your OH minus will be separated out. Now this OH minus will then interact with H plus to form water. So this is anion exchange, right? Here what is getting exchanged? OH minus is getting exchanged, and here what was getting exchanged was your cation. So that is why that is cation exchange resin and that is anion exchange resin. Just go through these reactions, not to be done again. What is the importance of last two reactions in cation exchange resin? I repeat, in cation exchange resin, the last two reactions means these two reactions, right? So what we have is RSO3H is the sulfonic acid group that gets first replaced with sodium. Once we have created a hydrocarbon network now with sodium, which generally is not the case, we do not generally get that. Now what we do is that RNA will be made to interact with your CaCl2. So CaCl2 का जो Ca2 plus है, that Ca2 plus will now get replaced with your Na plus. So your Na plus salt you know is soluble, and your R2M can be separated out. Now there is an advantage that whatever hydrocarbon is left can also interact with the rest of the Ca2 plus or Mg2 plus, whichever is left in the solution, to form your Mr2 again, right, plus H plus. अगर मान लो ये सोडियम में कुछ नहीं भी convert हुआ and you had the hydrocarbon part left, that hydrocarbon part will interact with M2 plus to give you Mr2, which can be separated out, because this is that big molecule that can be separated out, and that Mr2 plus it gives you another cation 2H plus, which can go into the water solution to make it pure. Okay? So now coming back onto the revision. This here what we've done is like two types of hardness. One is the permanent hardness and the other is temporary. Temporary is because of bicarbonates, primarily because of bicarbonates, and it can be removed by boiling. से क्या होगा? You will get either the magnesium hydroxide or you will get calcium carbonate. What is the purpose of getting calcium carbonate? That's not good, but it forms a precipitate which can be separated out and you get the hydroxide. Clark's method bolte hi, what is the compound that you should remember? Slaked lime. So you treat your hard water with slaked lime. What is slaked lime? CaOH twice, and the moment you interacted with CaOH twice, your hardness gets removed because you get a sodium salt probably, which gets easily it is soluble. Yeah. Then we have permanent hardness. Now permanent hardness is because of the presence of chlorides and sulfates of calcium and magnesium. Calcium magnesium का कोई भी salt है तो it is making your water hard. What is the disadvantage of hard water? It will form, why it will form scum. That is the insoluble stearate part of it. So it will form scum, which is what we do not want, and that wastes your soap also. So loss of soap means loss of money and so many other things. So how can that permanent hardness be removed now? First of all, we think about treatment with washing soda. What is your washing soda? Na2CO3. Forget about the reaction. Now Calgon's no, don't forget about the reaction. Just go through the reaction once. Then we have the Calgon's method. Calgon's method is treatment with, that is sodium metaphosphate. This is important because Calgon का main reagent याद होना चाहिए. बाकी reaction का go through मान लो how it just works. Right now, when do you have the time? I know you all are very busy at home also otherwise. So Calgon method is you have Na6P6O18. Right? Now the next is the ion exchange method. That is either a zeolite or a permutate, which is sodium, aluminium, NaAlSiO4. That is generally written as NaZ, and then there is just an exchange of ions. Wo Ca will get replaced with Na, and the rest of it can be removed, whatever is formed. Synthetic resin methods, we have discussed two methods. One is the cation exchange method, and the other is the anion exchange method. In the cation exchange method, it is generally the resin that we are using, the synthetic resin that we are using is a big organic molecule with, in cation resin with an SO3H, and in anion resin it is with NH2 or OH minus. Right now in cation exchange resin there is exchange of cations. So Na plus is getting exchanged with your Ca2 plus or Mg2 plus. In anion exchange method, it is your OH minus ions which are getting replaced with Cl minus or SO4 2 minus. Clear with it? So these are the methods of removal of hardness. So I hope I'm giving, as I'm rubbing the board in 2 minutes, you revise all these methods once again so that you memorize them once and forever. Yeah. Okay, now done? Need another half a minute? So that 10 years down the line, if I meet you somewhere, I'll ask you how to remove permanent hardness if I forget. Because I may age and you may grow younger and younger. Okay, question, what type of water forms comes with soap?
Hard water.
Simple. Alright, what's the formula of Calgon?
Na6B6O18.
Very good. Na6. You don't even need a mic, so your voice must be audible. Okay. What is the anion which is used in case of an ion exchange resin?
OH minus or NH2.
What do they get replaced with?
Cl minus or SO4 2 minus.
And what is the reagent that is used for the ion exchange method?
Zeolite or permutate.
This process is also called permutate
Permutate
process.
process.
Okay, so now we move on to the next topic, that is hydrogen peroxide. In hydrogen peroxide, as you know, that's another compound. Now we've talked of a number of, starting from hydrogen atom, and we've seen the entire quantum mechanical part of it, the structure of hydrogen. What are the two types of hydrogens that we did talk about?
Orthohydrogen and parahydrogen.
I was talking about hydrogen atom. But dihydrogen parts are orthohydrogen then, and what are the three types of hydrogens I should have said?
Protium, deuterium and
Protium, deuterium.
tritium.
Which is the radioactive one?
Tritium.
Very famous question. And then we have the dihydrogen. After dihydrogen, what did we talk of? Hydrides.
Hydrides.
Did we talk of anything else before that? Did we talk about water, heavy water? No. Deuterium? No. Specifically? No.
No.
Hydrides. What are the three types of hydrides that we did talk about?
Ionic hydrides, covalent hydrides and metallic or
Ionic,
interstitial.
covalent and interstitial. This we had done yesterday. What we've done today is just water, right? We've laid emphasis on water, and now we are moving on to the second compound for the day, that's hydrogen peroxide. And as I stated, it was like, no, for hydrogen peroxide, I did not state before, it has been discovered by Thénard, and uh, it is like useful for pollution control treatment of domestic and industrial effluents, that I'll explain how. Because these days, if you have the hydrogen peroxide given into the atmosphere, it's less harmful than your nitrogen oxides and sulfur oxides. Why are nitrogen and sulfur oxides harmful? Because they actually pollute the air in the form of, they can always form other non-metallic oxides which are harmful, that's one. And then when it precipitates, that is why it is said that you should never get drenched into the first rain of the season. Why? Because it is generally acidic in nature. Why is it acidic in nature? All the non-metallic or the pollutants get washed off, that's one thing. The second thing is uh, they get washed off completely. The second thing is that your non-metallic oxides generally interact with water to form acids, which then results in the rain to be acidic. So that, does that mean that it should not rain at all? It should rain to wash off the pollutants. So first rain is like always good. But ideally speaking, these days Delhi is so polluted, not even the second or the third rain or the fourth rain is like beneficial. So do not adopt any of those methods. Now we talk about the hydrogen peroxide and the preparation methods. So let's talk about straight away with preparations. The first one is you actually, by the action of cold and dilute sulfuric acid on barium peroxide. Now what you have is hydrated barium peroxide is BaO2 dot 8H2O, that is hydrated. Now you know the meaning of hydrated. So hydrated barium oxide plus, so it is the impact of this acid onto the hydrated barium peroxide. So you have BaSO4 plus H2O2, and this is what we want, plus water. Remember that these reactions are just to be gone through. So just have an idea. When your acid interacts with barium oxide, so that the moment you get that such a question in the paper, you will immediately recall that you had done it at some or the other point of time. So go through more and more data as much as possible, just go through it. Then the electrolytic oxidation of acidified. The second method is electrolytic oxidation of acidified sulfate solutions. So acidified sulfate solution means you have HSO4 minus aqueous and you are carrying out the electrolysis of it because it is electrolytic oxidation, electrolysis of it to form HO3 SOO SO3H aqueous, which on hydrolysis means reaction with water, gives HSO4 minus again plus 2H plus H2O2. All you need to remember is that you're getting hydrogen peroxide by the electrolytic oxidation of sulfates. So do not get shocked or worried by looking at the reactions just like that. The laboratory preparation of there is like the heavy hydrogen peroxide also, which is generally formed, and that is like simple the reaction of, this is one lab preparation. There is another lab preparation of D2O2, that is K2S2O8 reacts with D2O to form 2KDSO4, that's your kind of KHSO4 only, plus D2O2. And then if one wants, you can always replace your D with an H. You can always replace your D with an H. Then the next one, you can just, on industrial, the industrial method of preparation, this is the lab method. The industrial method of preparation is from 2-ethyl anthraquinol. 2-ethyl anthraquinol. 2-ethyl anthraquinol. That also just note down, just on interacting with simply oxygen or air, that will give you your H2O2 plus the side products. This is like all I want you to note down. That for the preparation of hydrogen peroxide, the very first preparation is a simple one, that is the hydrated form of your barium peroxide reacting with a mild acid, that is H2SO4 to give you H2O2. The second lab method, just go through it again, that is electrolytic oxidation of sulfates. Alright, simple electrolytic oxidation of sulfates. And then there is another lab method that is possible to prepare your D2O2, where your D can be replaced later with an H. So that can be done by simple replacement reaction. So K2S2O8 plus 2D2O giving 2KDSO4 plus D2O2. And then the last is the industrially important method, that is 2-ethyl anthraquinol for the preparation of hydrogen peroxide. Okay, so that is another one. Now let me tell you that in all these methods, hydrogen peroxide that is generally obtained is just 1%. What does 1% mean? 1% means that it is just 1% of the total aqueous medium. So how can you increase the concentration of hydrogen peroxide? That is by refluxing it at a very high pressure. You can note down that it is generally 1%. So if you want concentrated H2O2 can be obtained by distillation under reduced pressure. Bring about distillation under reduced pressure. It can be done by distillation under reduced pressure. Then the physical properties, I'll just read it out to you, otherwise no such significance. Remember that hydrogen peroxide is soluble in water. Hydrogen peroxide is soluble in water, alcohol and ether. So it is totally soluble in all proportions in water, alcohol and ether. It is a syrupy liquid. So how are you saying? Yes, you've touched it. It is a syrupy liquid, okay, and it is more viscous than water. See, viscosity, have you done viscosity? Viscosity is related to association of the molecules. So greater the association within one particular molecules with greater will be the viscosity. So if H2O2 is more viscous than water, means that the association of one H2O2 molecule with another H2O2 molecule by hydrogen bonding will be more, because hydrogen bonding as it is lead to viscous solutions. Okay? Then the strength of H2O2 is generally expressed in grams per liter. So there is a question here. That says that states that calculate the strength of 30 volume solution. Just note down this question. 30 volume solution of hydrogen peroxide. Please note this question down. Calculate the strength of 30 volume solution of hydrogen peroxide. For this, first of all, just note down that 30 volume solution actually means that 1 liter of this H2O2 solution will give you 30 liters of oxygen. Will give you 30 liters of oxygen at STP. Please make this question as an important one asked in the examination also. Calculate the strength of 30 volume solution of H2O2, and remember that 30 volume solution of H2O2 means that I am talking about that 1 liter of H2O2. 1 liter of this 1 liter solution, it just means that 1 liter solution of H2O2 will give you 30 liters of oxygen at STP. So if you talk about the decomposition of H2O2, the decomposition of H2O2 will be, it gives you 2H2O2 plus 2H2O, oh sorry, it gives 2H2O plus O2. This reaction is clear to everyone? So here I can say that what is the molar mass of H2O2? 16 to the 32 plus 2, 34 grams. So 2 into 34 grams is equal to 68 grams is gonna give me 22.4 liters of oxygen. Right? So from here I can straight away write it as 22.4 liters of oxygen at STP. 22.4 liters or 22.4 liters of oxygen at STP is obtained from 68 grams H2O2. Now, therefore, 30 liters will be obtained from 68 upon 22.4 into 30 into 30. So, right? And we want the strength of 30 volume solution. 30 volume solution means of 30 liters of oxygen only. We wanted the strength of 30 liters because what I stated here is that 30 volume solution of H2O2 means that 1 liter of H2O2 gives 30 liters of, is equivalent to 30 liters of oxygen at STP. This is what I want you to remember. I am time and again telling you that. So 30 liters is equal to what? You can just simply calculate. Roughly it is given as 91 grams. So therefore the strength of 30 volume of H2O2, 30 volume of H2O2 means 30 liters of O2 is equal to 91 grams per liter. I just want you to understand the first statement in details. That whenever you have 30 volume means 1 liter of H2O2 is giving you 30 liters of oxygen. ठीक है? अगर ये यही होता 50 volume solution of H2O2, that would have meant 1 liter of H2O2 is giving you 50 liters of oxygen. ठीक है? ये चीज समझ में आई है तो rest is like your unitary method only. So that can be done. We'll take up another question, but before that just one last topic of heavy water. Let's talk about heavy water also. Heavy water is nothing but you have normal water is H2O. What is your heavy water? That is D2O. And let's talk about the preparatory methods. And remember that whenever the last compound that we did talk about was hydrogen peroxide. Whenever we talk about hydrogen peroxide, it has the property of decomposing itself into water and oxygen. ठीक है, decompose मतलब अपने आप को it will break down into smaller molecules. So H2O2 will break down into H2O2 plus O2. ठीक है, but this reaction happens with an explosion, and this is generally supported with impurities. So that is why H2O2 is always kept away from dust. Because if it is kept in impurity, what will happen? It will go into an explosive self-decomposition reaction, which will be dangerous. So that is one thing. Now we were talking about what? Heavy water. Heavy water is your D2O, and I did tell you yesterday who discovered D2O. That was Urey in 1934. He got a Nobel Prize for that. So he discovered heavy water. And then we talk about the preparation. The preparation is first one. I'm just putting down the methods of preparation of D2O. First one was exhaustive electrolysis of ordinary water. Electrolysis of, now you must be wondering, ordinary water has just H2O, but it was shown that ordinary water has some small fraction of D2O also. जो normal water होता है उसमें there is some small fraction of D2O which is present in it. So what happens? H plus has the tendency to travel faster. ठीक है, तो हम क्या करेंगे? We'll bring about exhaustive मतलब prolonged. Electrolysis करते जाएंगे. So H plus has a tendency to move faster. So H plus will be liberated as H2 at cathode. ठीक है? H plus is positive. Positive means cation. Cation will go to cathode. Cathode is negatively charged. So H plus will immediately go on getting liberated at cathode. H2 gas निकलती जाएगी. So पीछे जो once your water has been completely electrolyzed, last में क्या बचेगा थोड़ा बहुत? D2O, and then that will get the remaining water is enriched in heavy water, and then you can actually prepare it. Another way of preparing it is by it is actually obtained as a byproduct of some fertilizer industries. It is obtained as a byproduct from fertilizers industries, and generally questions like this are like not asked because you do not have any chemistry specific thing here. Fertilizer industry again byproduct क्यों? क्योंकि पानी में D2O होता है. Once your main water has been utilized and subjected to pressure and temperature conditions, because H plus travels faster, so it will exhaust itself first. तो बीच में बचेगा जो वो होगा D2O. So normally whatever water is left after treatment of preparation of fertilizers, whatever water is left is enriched in D2O. I would not say that it is completely heavy water, but it's called heavy water because now D2O concentration is more than the H2O concentration. Okay, now the uses. These uses of heavy water are important, and this you will be doing also. It is used as a moderator in nuclear reactors. Moderator का मतलब मैंने क्या बोला है? D plus has the property of moving slowly, and moderator has the, what does the moderator do? If two friends are fighting, what does a moderator do? It slows down settles down the matter or slows down the matter. So here it will slow down the movement of the fast moving neutrons in the nuclear reactor. Neutrons, and controls the nuclear fission process. So moderator controls the nuclear fission process. Fission मतलब बड़ा nucleus breaking down into smaller ones. Then it's used as a tracer compound. Tracer compound is generally used to elements present, and generally it is used for the compounds which are very short lived. So tracer compounds are generally used in reaction mechanisms. It is used as a tracer compound in reaction mechanisms, क्योंकि mechanisms जब हम लिखते हैं तो उसके बीच के जो short lived species होते हैं ना, क्योंकि final product तो हमें मिल जाता है when the reaction is complete, जो short lived intermediate species होते हैं उनको trace करने के लिए we make use of heavy water. Okay, it is used for the preparation of deuterium compounds. So D2O, say we can prepare deuterium containing compounds. So how can it be prepared? Instead of water, now you treat your stuff, whatever salts you have, with D2O. Jaise for example, you want a deuterium containing compound CaC2 plus D2O. The reaction will be absolutely the same as that of water only. जैसे water interact करता है वैसे ही D2O करेगा. So what in this case you will get? You will get Ca. You will have Ca calcium hydride. This is calcium carbide. So you should get calcium hydride. The reaction is wrongly given here. So this is CaD2 plus you will have CO2. Balance kar lena please. So here what we have is you have CaC2 plus D2O giving CaD2 plus CO2. Okay, let's take another one. SO3 plus D2O. What will it give? सिर्फ H2O को उसकी जगह पे रखो, H की जगह D लगा दो. That's it. So you will get D2SO4. All right. Last but not least, we have talked about this also. What is this? We are talking about D2O. That's heavy water. Heavy water, how is it obtained? It is obtained by exhaustive electrolysis of ordinary water. It's याद नहीं रहेगा मुझे पता है, but then exhaustive electrolysis तो याद रहेगा because उधर से we generally get our H2 and O2. Electrolysis of water, so what do we get? We get H2O2. Exhaustive मतलब you carry it out in an exhaustive manner ताकि जो भी last में we have is gonna remain as D2O. So that's like an prolonged. So whatever water is like left over is enriched in D2O. Then you have byproduct का भी same funda. Then it is used as a moderator. Moderator use is one of the best uses. It will slow down the fast moving neutrons in case of a nuclear fission process. So nuclear fission reactor mein it is used. Then you have it is used as a tracer compound for the reaction mechanisms to trace your short-lived species. Then it is used for preparing deuterium containing compounds, and for which you've written down the last reaction on your own, that gives you D2SO4. Okay, yesterday we did talk about dihydrogen also, and when we talk about dihydrogen, let me tell you it is very important as a fuel. Dihydrogen is very important as a fuel. It is used in rocket fuels. Alright, liquid dihydrogen, we did this yesterday, did we? Now these days hydrogen economy is like really very important, that I noted down, because it is used along with CNG also. Your dihydrogen is actually mixed with CNG. This is something that you should know because questions from latest things do come up in your exams, especially entrance exams. So what we have is, if you have a dihydrogen mixed with CNG, the pollutants that are released into the atmosphere are less harmful than in otherwise. CNG as it is considered to be better than your petrol and diesel combustion. So in the rest of the cases what we have is, if you mix up your dihydrogen with CNG, earlier it was just 5% of it, now they are increasing the percentages because it was considered to be difficult to handle dihydrogen at a human level here. That is why it was used in rocket science, but now not rocket, I mean generally that word is used in English. It is generally used as a fuel in rockets, but now it is used even in our normal for our normal transportation. So that's another use. All right, can we have the next slide so that we can just discuss questions? Just giving you exactly 1 minute to go through whatever in hydrogen we've done till now. Kuch reh gaya? Is there anything that is left? Anything left? Yes. For preserving we used urea. Urea is NH2CO NH2. What it does is it saves H2O2 in the form of, it forms a trap for the H2O2 and it encloses it within it, and then it does not allow it to get decomposed, otherwise it lowers down its reactivity also, because see, if you have the structure of H2O2, it will get involved in hydrogen bonding with urea. It has NH2 minus part is there, and then you have the NH2, CO, NH2. The CO part of it will get, or the O will get attached to the hydrogens. The NH2 minus will probably interact with the H plus ions. So that way it gets temporarily bonded to your H2O2, from which it can be easily recovered. Whatever are the storage agents are generally those which form temporary bonds with your molecules and which can be broken down later. Is there, but not to the extent of a very strong one. It is only a temporary interaction that plays a role here. Sorry? So that is because, you know, decomposition is initiated. There are certain reaction conditions which cause about the activation energy of the molecule to be crossed. What is your activation energy? Like for example, I'll come to this question. Like activation, first your question. Like what you have is the activation energy. यहाँ पे आपके reactants हैं, ठीक है? यहाँ पे आपके products हैं. Now in order to form the products, your reactants need to cross this energy barrier. How this energy will be provided depends upon what are you providing to it. Sometimes you provide light to it and the molecule gets excited. सिर्फ light से, because light में भी तो radiation है. Radiation का मतलब energy है. We understand all that. Now you're science students. So what you have is you provide energy in either in the form of light or in the form of temperature or in the form of some other chemical reagent that triggers with your reactant, and once it crosses the energy barrier, then it leads to the formation of products. So even in light, what happens is for H2O2, it initiates a process of decomposition, so that is why it's kept away from it. Okay. Then what we have here is this is just revision for you. Heavy water is what? It is deuterium oxide, and now you know about it all. How is it prepared? Exhaustive water, and then you have some fertilizers. Very nice. And when we talk about the uses, we have moderator in nuclear fission reactors. Then a tracer compound in reaction mechanisms. When we use it for the preparation of deuterium compounds, there was a question there. That question was, that suddenly reminds me that somebody had put up a question. In the reaction of CaC2 plus D2O, it gives CaO plus C, oh yes, it gives C2D2 as written in NCERT. That's right, I'm sorry. I wrote it as Ca2. Now this is like, yes, this is the right reaction. Thanks for correcting me, because here it is not CaD2, but you get actually a compound of C2 carbon hydride, which is C2D2 plus CaO. So thanks a lot. Right, so that was just a correction. Please make it that it is generally the compound of deuterium formed with carbon, which is like C2H2. What is your C2H2? That's acetylene. You have CH triple bond CH. So it is just the same compound. Too much of chemistry of hydrogen. So it is DC triple bond CD, which is formed in this case, which is really important when you react it with this. So it is C2D2 plus CO. Thank you. Okay, so now when we talk about it is used for the preparation of deuterium compounds, and for the preparation of deuterium compounds, if it reacts with calcium carbide, what does it form? C2D2. C2D2 plus calcium oxide. This was a very important reaction. I just fumbled when I wrote. Okay, next. Now whatever we've discussed till now, we have discussed the volume strength of H2O2. That was when we talk about volume strength, whatever volume strength is asked, that means that 1 liter of H2O2 is giving you that many volumes of O2 at STP. Then we've talked about hydrides, 3 types of hydrides: ionic, covalent and metallic. Covalent also are of 3 types: electron deficient, electron precise and electron rich. Alright, then there is another one that you talk about the degree of hardness. See, degree of hardness depends upon the salts which are there, which are present. If the concentration of salts is high, then the degree of hardness is also high. Because if you sometime get your water tested, these days you get a hardness parameter testing kit. So you insert it in water and it will give you the hardness parameter in electronic digits. So the hardness ranges till 100 or sometimes even more. So hardness is like a parameter which only tells you about the concentration of the salts which are dissolved in it. So, and hardness is important also. Hardness is to some extent is good because you need to have some salt, but the only thing is it does not produce lather, which soap is another demerit. Then it produces scaling with your boilers, that is another thing. And then when we talk about degree of hardness, we talked about permanent and temporary. Permanent can be removed by 4 methods. The first method was with washing soda, second was with Calgon's method, third ion exchange resin and synthetic resin. For removal of temporary hardness, we had boiling and Clark's method, that is with slake lime. Then we did talk about the isotopes of hydrogen which were protium. Radioactivity also exists on only one, which is tritium. Allotropes of hydrogen are your orthohydrogen and parahydrogen. Ortho are the ones in which both the hydrogens have the same spin. And then you talk about reactivity order of your nascent hydrogen, that was a newly born. We did talk about the atomic hydrogen, and we talked about the dihydrogen. Which was the most reactive of them all? No, we talked about the atomic hydrogen, nascent hydrogen and dihydrogen. Okay, just check that up once. And then in that case you have the nascent hydrogen to have lesser reactivity than your atomic hydrogen, because atomic hydrogen immediately gets converted back to dihydrogen, releasing a lot of energy. That reaction was highly exothermic, right? Then we move on to heavy water. That was the last topic that we just covered. Then this is also important. Metals of group 7, 8, 9 do not form hydrides. These are the non-metallic parts. They generally do not form hydrides. And even in group 6, you talk only of chromium to form a hydride, right? But here we've just seen, we talk only of chromium to form hydride here. Because when you talk, do not mix carbon with it, because carbon has a separate branch totally when it deals with the hydrogen part of it. That's hydrocarbon chemistry or the organic chemistry that you're doing. So remember that metals of 7, 8, 9 generally do not form hydrides. This is known as the hydride gap. This is known as the hydride gap. They do not interact and form. Then you have talked about the hardness removal methods, and then this is just a recap of what we've done before. Structure of hydrogen we've already discussed. Then similarity to alkali and halogens were the very first thing that we started up yesterday with. There are similarities, whereas there are dissimilarities also. Dihydrogen and preparations we've covered. Your syngas was CO plus H2. Then in hydrogen economy, I just talked about it being used as a fuel. And then you talk about water. In water is like an intricate and an extensive topic that we've just discussed. Hardness, we've discussed heavy water. Hydrogen peroxide is done. And in hydrogen peroxide, we've just done the method of preparation and the uses by and large. And then that sums up your chemistry of hydrogen. And now let's take up some questions. Structure of, when you talk about the structure of, we'll just take it up in the questions. It is coming up in the questions also. Let's talk about the questions first. Just 15 minutes left. Let's take up some MCQs. Then, yes, please note this down very importantly. What we have is the volume strength of hydrogen peroxide is equal to 5.6 into normality. This is generally the you have the strength given as 5.6 into, this is just a shortcut formula. And then you have, if you are given the percentage strength like 2%, 3% of it is like already the strength given, then you can use the formula as 5.6 into percentage strength upon equivalent weight. Hope you remember normality. It is the given mass upon the equivalent weight upon the volume of solution in liters. Number of normals per liter of solution, and that into 10. It's all taken into consideration when you employ the entire formulae. And then the volume strength of hydrogen peroxide is nothing but 11.2, Why 11.2? Because in this case, what you have is, it is 11.2 into molarity, just the double of it, molarity. And then you have the same formula applied for the this. Now let's come on to the questions. Some bit of the questions that we can just quickly do. All right. Look up and be quick in answering the questions. Another 15 minutes that we have. What is the half-life period of tritium? Not given to you. So what will you do in that case? I have given you the tritium, and why are we talking about the half-life? First tell me. Because it is radioactive. And the formula for half-life is T half is equal to 0.693 upon K. Repeat it. What is the half-life? 0.693 upon K. Alright. So half-life in this clear case, please note it that it is 12 years. 12.33 years. The half-life is 12.33 years for tritium. And that is like you just need to just go through it once so that you remember it. Then the next case. You tell me quickly. Zinc plus NaOH is gonna give you what? Yes. Because zinc, this reaction we had just taken and gone, just go through it, and you will immediately get to know that in this case normally it is for the production of H2. So H2 is being produced in all, but you have to take care of the rest of the reagents also. Let me tell you, it's a common sense question. You don't need to remember that whether sodium zincate was produced or not. Why don't you need to remember? Because first of all, H2 is getting produced is all you remember. Then you get confused in the first three, right? Now whatever is left over has to be accommodated in the side product, or else they should have given a third product here in the first and the second case. So H2 plus you have NaZnNO compound, which is Na2ZnO2. So that is like a common sense answer, not from the memory. Maybe you remember that it's sodium zincate, but otherwise you can simply apply your mind that zinc when is treated with a base gives you dihydrogen. This was a method of preparation you had done. Dihydrogen to तीनों में आ रहा है, side product तो याद किए ही नहीं है. So nothing to worry. If they are giving the side products, they would have given the third one also. So in that case, you accommodate all the rest of the elements which are taken care of only in C option. So it will be sodium zincate and hydrogen. Next. So the third question is, it talks about which element forms electron-rich hydride. Now this is the one which will already have extra electrons. Oxygen. For calcium, it will form, what kind of a hydride will calcium form? Electron precise. What about boron? Electron deficient. Aluminium deficient. So you should be able to signify each one of them with that. Then the formula of calgon. Na6P6O18. Alright, next. Among the following, which is the interstitial halide? Now, here there can be a confusion also. They are calling it interstitial hydride, लेकिन यहाँ पे कोई stoichiometry दे नहीं. अगर इतने intelligently वो stoichiometry देते, so the answer would have been given. So here, because Ca exists as H2, so it would be wrong to give CaH 0.26 or 2.26 as the. Remember that it is only the lanthanide and inner transition elements which are involved in the formation of interstitial hydrides. So here you have to understand for yourself that LaH3 is the only option which is involved. LaH3 is the only option involved. What I wanted to lay emphasis on here is to just remind you that if they are giving it as LaH3, it is not wrong to give LaH3 here. It is not wrong to give LaH3 here, simply because of the reason that when you talk about the non-stoichiometric compounds, as you are doing in your solid state in class 12th now, you talk about a compound like FeO. So this will form a non-stoichiometric compound. Why? Because this FeO will comprise of a mixture of Fe2 plus and Fe3 plus. Somebody had asked yesterday and I had taken it up also. So it will be a mixture of Fe2 plus and Fe3 plus, because of which it may form a compound like Fe.96O. Got the point? So if they're asking for any interstitial compound, it is not wrong to give that this will be the one which is capable of forming an interstitial compound here in this case, and an interstitial hydride in this case. Okay, next question. What is the amount of oxygen liberated at STP by 30 volume of 1 liter solution of hydrogen peroxide? And I repeat that this is a direct question, but otherwise you can get it in the form that we have taken up. Simple, but it's like to the point. So you can be asked for any amount. Right? Next question. So the answer was C in that case. Then we move on to the question number 7, that is, among the following, in which hydrates water molecules only occupy the interstitial site? Now you have to think about it and tell me. In which of the compounds that the water molecules will occupy interstitial compounds? See, many of you, when you get confused, you straight away go to D. Please do not do that. कि सारे ही होंगे शायद. Do not go by your instincts for the entrance examinations. Do not go by inky pinky ponky. So you have to just apply your mind to each one. Does this belong to D element? D block. So this is a coordination complex, straight away out. So all of these bhi gaya, straight away bhi gaya. So 50-50 option used, right? Now copper sulfate dot 6H2O. यहाँ पे it looks like, you know, it may be a water of crystallization, because water of crystallization is the one which will come into the interstitial sites. ठीक है ना? Water of crystallization जहाँ जहाँ पे है, there it will come into the interstitial site. So there is a possibility that this or this may be there. But again, this is what? D block element. So it has the property of forming the coordination complex also. So what are you left with? So the answer in this case will be BaCl2.2H2. Now next, which property of hydrogen makes it to resemble with halogen among the following statements? Go through the statements carefully. Which property of hydrogen makes it to resemble with halogen among the following statements? First one is hydrogen has a strong, see, all the statements are true. I don't know, I'm sorry because I use the color in such a way that it's not readable. Hydrogen has a strong affinity for non-metals. It does have. Otherwise, not a very strong affinity, but it reacts with non-metals. High ionization potential is also correct. What is the order of the ionization potential for hydrogen? 1312. And what is it for the halogens? Halogens is 1600 something, because there is only a difference of 300 kilojoules. And what is it for alkali metal? It is 512 something. So 500 something. So it has a high ionization potential, matches up with your hydrogen, that makes it resemble your halogens that we considered yesterday. Hydrogen has a low value of electronegativity, and then you have hydrogen acts as a reducing agent. So many of the statements actually you find that may be correct, but you have to look for the most appropriate answer to your question. Next, then you have, which of the following is an electron precise hydride? This is clear cut. We've just discussed it. So it's like taken from one part. Demineralized water is obtained when? Demineralized water is obtained when? Did I mention cation exchange or an anion exchange resin? We get, see, demineralized water, we have 4 methods of removing permanent hardness. The first one was like, second was like Calgon's method, third was your zeolite method. In all these, we just stated that they're just going to remove your calcium and magnesium. I did state that there is an advantage of using the synthetic resin method. The last one that we've done was the synthetic resin method, in which it not only removes the ions, cations or the anions of your hard part, but also all the unwanted cations and anions can also be removed. How? Because it generates an extra H plus, it generates an extra OH minus. So that removes the unwanted cations and anions also. So in the first case of cation exchange resin, you used SO3H. In case of anion exchange resin, you made use of NH2. So that forms your second option, that is your NH3OH resin also and SO3H resin also. Both these methods fall under synthetic resin, so the correct answer would be the one in which it is like water is passed through SrSO3H resin and RNH3OH resin also. Alright, is that clear to everyone? Then let's move on to more questions then. Will you be able to read it? No, no, no. So I think I will read out the questions for you. I don't think you will be able to read it out from here. Several assignments are like given here. I move on to the first question. Okay, the ionization energy of hydrogen is high as compared to alkali metals because small size. Clear, everyone? Then move on to the next question. I like your spontaneity. Which of the following is the correct statement? Read out the statements completely. First is true or false? False. Second, hydrogen has a strong tendency to gain one electron. Same. Second is true. Second is wrong. Second is a strong tendency to gain one electron, which is the same as that of the alkali metals. Alkali metals give, take. So here. And then the third one is hydrogen is diatomic, so are halogens, which is like correct. Okay, let's move on to the next question then. Isotope of hydrogen, which is radioactive, is tritium straight away. Then the next question, the isotope of the hydrogen accepts an electron to uh, to attain inert gas configuration in this way. Halogens, simple. So you have, if at all you get a question from hydrogen chemistry, feel lucky because the questions are going to be as simple as this one. Hydrogen acts as a reducing agent and thus resembles alkali metals. Very good. Which position of hydrogen explains its properties? At the top of halogens or at the top of alkali metals? Which position of now many of you will write it down as you expect, as you've seen. It is on top of the alkali metals, but which correctly justifies? Both on top of 1 and 2 because the number of properties that it resembles are equal for both. Right? So both on top of 1 and 2. Ionization energy of hydrogen is, I'll read out the options if you miss out the fourth one, that's much higher than that of fluorine. Ionization of, now I'm reading out the fourth option is much higher than that of fluorine. Just in case if you like it. Ionization energy of hydrogen is equal to that of fluorine, lower than that of fluorine, slightly higher than that of fluorine, and much higher than that of fluorine. Why are you thinking? Lower than that of fluorine because you know the values. ये तो 1300 के आसपास है and fluorine is around 1600. So straight away. Then we come on to the next question, that is the catalyst used in, no. Which of the following statements concern the protium connected with the protium, deuterium and tritium is not correct. They are isotopes of each other is correct. They have similar electronic configurations is correct. They exist in the nature in the ratio of 1:2:3 respectively. Exist in nature matlab abundance. Ki hydrogen exists as 1, deuterium is double and protium is triple. Is that correct? No, so false. So straight away that's the answer. Next question. Number of nucleons in D2 molecule is. Nucleons is a combination of electrons plus neutrons. Protons plus neutrons. Yes, otherwise the correction. It is protons plus neutrons. Okay. So that is protons plus neutrons. So how many? 4. Clear to everyone? Water gas is CO plus. That's very simple. So the next one, the catalyst used in water gas shift reaction is very good. Water gas shift reaction is the one in which we had used CO plus H2. Alright, so that's nickel. The next one, the reaction between which of the following reactants produces hydrogen? First, because we've talked about only zinc. Will pure zinc give it in this case? Why? Why? Because zinc is a slow reactant. You generally talk in terms of chemistry and zinc is a slow reactant, so it will not give you immediately. Then the next question, high purity dihydrogen is obtained by electrolyzing High purity dihydrogen. Yes, we did it yesterday. We do get brine solution, but the very high purity is also obtained from warm aqueous barium hydroxide. So according to me, both should be marked. The correct answer is given as 1. The correct answer is given as 1. We'll just check it once, right? Because according to me, even brine solution, when we did it for NaCl, and when we talk about the electrolysis of that, it does give us to a very high purity of 99.98%. So we need to check whether that gives 98.99%. So that is all that is need to be checked. So between these two, there's a discrepancy. Will be solved very shortly. All right, next question. Hydrogen is not obtained when sodium reacts with, no, here in this case, sodium, when it will react with, see, sodium is a metal. When it reacts with H2SO4, there are chances of H2 getting emitted. When it reacts with dilute HCl, there are chances of getting H2 emitted. When it reacts with cold water, that's again H2O. So chances of H2. Where will H2 come from? NaCl. जब H है ही नहीं तो वो आएगा ही नहीं. वो ये question तो करा ही नहीं था. You got the question? Because simple questions are made a little twisted so that it is not directly up to the mark. Because in entrance examinations, elimination is more important for the selectors than the selection. So here what we have is, you have hydrogen is not obtained when sodium reacts with molten NaCl. कहाँ से आएगा hydrogen? Then the process by which ammonia is formed for nitrogen is known as Haber's process. Question number 16, I'll read it out for you. Hydrogenation of alkenes yields alkanes, alkynes, alkenes. All right, I take a break here. There are more questions to it that you can take up from the presentation and then can solve and get back to me on through mail so that I can just correct them. I gave you assignment right at the beginning of 11th standard once. You remember? I'd given it once. Never followed it up. So now I think you need to tighten your seat belts and then start working right from day 1. One has already gone, so whichever moment you start up with. So all the best. Thank you.